20, this direction 4, and then this direction 20. And S equals 44 total. What I showed, and I'm happy with that, is just to show that, because this is serves a purpose, but I'm more interested in time, I think. So 2 seconds, it goes this way. First second, a second, so t equals 0, t equals 2. In just the time. This is only for the time capsule if you want. And then between 2 and 4, it goes this way. So 2 seconds, and this is t equals 4 seconds. And then 2 more seconds, it goes this way. So this way and this way. And this t equals 6 seconds. So this is just for the time, which I'm happy with. To show the distance and time together, we have to measure, right? So I have to say that this is 10 meters and this is 10 meters. Then it goes back 4 and it goes back 2. The positive direction, another 20. And it reaches at this point 6 seconds. After 6 seconds, the total distance covered is 44. That's what it's just a diagram showing what the direction and the time. If you want to show just the time, this is good enough. If you want to show both, again, you have to make a corner. And how do I really show the corner? And I have to make a corner. So I know they show in the book something like this, but what does that signify? And I should put them one on top of the other. So it goes 2, and then 20 meters, and then it comes back 4, and then it goes back 20 meters. So this is what I should show, but I can't because nobody understands if I do this, right? So again, just imagine that it turns, but it's basically on the same direction. Turns here, not here, and not here. So that's why I showed only the time, what happens. And the final question here is, when is the particle speeding up and when is the particle slowing down? And we already have this, and I have to copy it. So the last part, t, and we have 0 and 2 and 4 and 6, and we have a of t, and we also have to look at a of t. So this is 0 here, positive, negative, positive. So now with a of t, and we have determined a of t. No, not yet. So the second derivative of t, that is 6t minus 18. And when we set this equal to 0, we get 3 seconds. So 3 is here. And since this is a linear function, it looks like this, from negative to positive. So negative, positive. So here it's slowing down. Here they have the same direction, speeding up. Here they have opposite, slowing down. Here the same, speeding up. Any questions? Is this what you meant? Is this what you wanted to see?
Yes.
Perfect. Is there any question?
No, that's pretty good.
Anything else?
If we don't have time for it, that's okay. I can just like watch the video on WebAssign. But could we go over question 6 on WebAssign? It's about a man walking one way and then a woman walking in the opposite way.
Yeah. Let's do it. No. That's fine. That's great. So you said it's 6 in, I'm assuming 3.9?
Yeah.
Let's take a look. Where is it? So 3.9, number 6. Okay. So if you want me to change any of this, I don't know which problem I'm looking at, so I have no idea. I mean, which of you has this problem? So man starts walking north at 4 feet per second. Okay, north, 4 feet per second from a point P. Fine. 5 minutes later, a woman starts walking south at 5. Okay, from a point 500 feet due east. Okay. Okay, south at 5 feet per second, and this is 500 feet. Good. At what rate in feet per second are the people moving apart? 15 minutes. Of course, everything is in seconds and they're throwing minutes at us, okay? After the woman starts walking. So she starts walking 5 minutes later. Okay. Do you want to change the 4? Do you want to change the 5?
Yeah, could we change the man walking north to 3?
Okay.
And the woman, her walk is 7 feet per second.
Perfect.
And then the 515.
515?
Oh, no, the 500 and the 15 stays the same.
Oh, okay.
So, yeah.
No worries. Perfect. So let me remove this so I don't confuse anybody. Okay, so here's the situation in this. She starts 5 minutes later. The woman. Okay, so let's make a different figure and talk about it and see what happens here. So I'm on page 5. Good. So the person who starts going north, let's say the distance covered by this person is y. So 3 feet per second must be dy over dt. No question about it. So this is a distance that is fixed, so it will be used in the problem. Now, this is, I'm going to call it W, and of course dW over dt must be 7 feet per second. Okay, so this person starts 5 minutes later. Because everything is in seconds, I'm going to say 5 times 60, 300 seconds later. We're asked to determine, I'm going to call this, I already called this W, I'm going to call this V. No, I don't want V because V stands for velocity. So let's find a different letter. I'm going to call it A. So we're asked to find dA over dt when t equals 15 times 60. Remember, everything has to be in seconds. So this is 900. Okay, so that's our question. And we know that this cannot come into play till the very end. So I'm going to imagine that I move this distance here. And I have this triangle. So this is still 500. This is the distance covered by the woman, which is also here. This is the distance covered by the man, which is this. And this is what I'm interested in. How fast is this changing when such and such? So I do have that a squared, Pythagorean theorem, a squared equals 500 squared plus y plus x. y plus w squared. So this is 500 squared plus y plus w squared. So then from here, sorry, I think I messed up this, hopefully not. Okay, so from here I can differentiate. And this is 2a dA over dt. This is gone. Plus, I'm sorry, I did not do plus. 2 y plus w to 2 minus 1 times dy over dt plus dw over dt. So then dA over dt, and I can get rid of this, is y plus w dy over dt plus dw over dt divided by a. Okay, what is a? A will equal the square root of this. So 500 squared plus y plus w squared. Now we have to be careful how we determine all this, because we have to remember that she starts 300 seconds later. Okay, so if we reference the beginning here, then her time will be minus 300. We can also say that his time plus 300. It's up to you. It doesn't matter to me. So we either say the time is t, and for him, and for her is t minus 300, because she started 300 seconds later. So for him, I use time t, but for her, I have to use t minus 300, because she used less time by 300. In order to determine, of course, w, and of course, y. So that's the only thing that we need to pay attention to. So let's see how we continue. So dA over dt, y. Okay, y is this distance, which is rate times time, 3 times, so 900 seconds from when? "15 minutes after the woman starts walking." Ah, so we have to add 15, which is 900, plus 300, because he already walked for 300 seconds. So in his case, this will be 300 plus 900. So his time is now, but I don't want you to think that I'm doing this at the beginning. I'm not, this is at the end, right? So he used the time of 900 plus 300 seconds, which is 1200 seconds. She used the time of 900 seconds only. So I don't really need this anymore. So her time for the woman is 900 seconds. But for him is 1200. Okay. So then we have here W. We have Y, which is, one more time, 1200 times 3 plus W, which is 7 times 900. Now, dy over dt is 3. dw over dt is 7. everything divided by, and now we need the square root of 500 squared plus this squared. So all this, but squared. So 3,600 plus 6,300. Okay, so can I clean it up a little bit before I put in the calculator? So again, I think this is, again, check my numbers always. So 3,600, and this is indeed 63. So I think that this is, right, is it 10,000, right? 36 plus, no, this is 9,900. Okay, so 9,900 times 10, okay, over the square root of 500 squared plus, again, I think it's 9,900 squared. Okay, so let's see what we get. I'm trying to clean it up a little bit before we enter it in the calculator. Okay, so let's see. What do I have? I have 9,900, and divide that by the square root of 500 squared plus 9,900 squared. Close. Okay. So 9.987. I don't know how they want the answer. We'll look in a moment. 9,873. And they want, where is it? Round your answer to 2 decimal places. So 2 decimal places, I would say 9.99. And it's in feet per second. Is this okay?